For centuries, humans have looked up at the night sky, trying to deduce exactly how our 4.6-billion-year-old rock actually formed. In 1796, mathematician Pierre-Simon Laplace updated Immanuel Kant's earlier ideas, arguing that planets simply condensed out of a slowly rotating, swirling cloud of material. By 1900, scientists Thomas Crowder Chamberlin and Forrest Ray Moulton offered a different explanation, leading to a wave of competing binary theories. They argued that a massive passing star approached our sun, and its sheer gravitational pull ripped away a cigar-shaped trail of material that eventually cooled and condensed into the planets. These early ideas were elegant, but they relied heavily on philosophical deduction. They lacked the hard physics necessary to explain the chaotic history recorded in the rocks beneath our feet. This historical diagram illustrates the orbital mechanics of our solar system. Researchers realized the numbers behind early theories simply did not add up. True planetary formation required a model accounting for the interconnected gravitational forces mapping these precise orbits. Building a planet is a process of destruction and reconstruction over millions of years. In 1950, scientists Otto Schmidt and Carl von Weizsäcker proposed that the early solar system was a chaotic, disk-shaped cloud of dust, hydrogen, and helium. Through a process called accretion, friction and particles colliding at high speeds fused material together, building up the hot, barren mass of the early Earth. How does a uniform ball of hot rock reorganize itself into a planet with functional layers? The answer is a structural sorting process known as differentiation. As the molten Earth spun, its internal materials separated by density. The heavy materials, like iron, sank inward to form the planetary core, while the lighter materials floated outward to cool into the surface crust. Without this internal density sorting, the planet would have remained a solid, inert rock. Differentiation was the first vital step in building a working planetary machine. To understand the Earth, we also have to look at its companion, the Moon. In 1838, Sir George Darwin suggested that the early Earth was spinning so rapidly that it flung a piece of its own mass out into space. He pointed to the massive depression of the Pacific Ocean as the literal scar left behind by the expelled rock. Modern planetary science entirely rejects this explanation. The accepted consensus today is an event commonly referred to as the giant impact, or the Big Splat. Roughly 4.44 billion years ago, a body the size of Mars slammed into the Earth. The collision blasted a massive ring of debris into orbit, which eventually coalesced to form the Moon. The sheer kinetic energy of this collision radically reheated the Earth, accelerating the internal melting and sorting processes that were already underway. The early Earth possessed a primordial atmosphere made mostly of hydrogen and helium, but those light gases were quickly stripped away by intense solar winds. To get the breathable air we rely on today, the planet had to produce a new atmosphere from within, through a process called degassing. As the solid outer crust cooled, massive volcanic eruptions vomited trapped water vapor, nitrogen, and carbon dioxide from the deep interior straight into the sky. Our current atmosphere erupted from the planet's own molten depths, a violent exhalation from the deep interior. As the atmospheric temperatures finally began to drop, those massive volumes of volcanic water vapor started to condense. This triggered millions of years of continuous rain. The water fell onto the cooling crust, pooling in surface depressions to create the Earth's very first oceans. Within this newly formed oceanic chemical soup, around 3.8 billion years ago, inanimate matter achieved something extraordinary. The fossil record shows microscopic structures where chemical reactions generated complex molecules capable of duplicating themselves. The microscopic origins of biology were only possible because of the precise, sequential timeline of geological cooling and atmospheric condensation that set the stage. Immanuel Kant imagined a peaceful, slowly spinning cloud of stardust. The reality we now understand is a history of catastrophic impacts, melting planetary cores, and explosive volcanic degassing. This planet operates as a massive convective engine. The extreme violence that threatened the early Earth provided the exact cosmic recipe required to forge our oceans, our air, and ultimately us.